All right, thank you. All right, so let's just do a quick review of what we did in the last lecture. So remember, this is in the contact setup, so as opposed to the symplectic setup from this morning. So M now is going to be an odd dimensional manifold. C is a contact distribution, and we fix the contact form alpha. And L is a legendrian submanifold. And we're interested in tame, almost complex structures, same as discussed this morning, on the symplectization of M. And we start by considering a collection of Reeb chords, an ordered set of Reeb chords, I should say. And by Reeb chords, again, I mean flows of the Reeb vector field specified by alpha. We define this moduli space of J-Holomorphic maps from the disk into the symplectization. The disk has some punctures and labeled punctures, where the first puncture goes to, there's some specifications on the boundary of the disk. First of all, the boundary has to map to this Lagrangian, exact Lagrangian submanifold, given as the cylinder over the legendrian. And then second, the first puncture has to converge to a Reeb chord at positive infinity, and the remaining punctures have to converge to Reeb chords at negative infinity. And there is an order here given by the boundary of the disk. So B1 comes first, and then B2, and so on. Okay, and then, so that's the moduli space of interest. If we were to do fancier coefficients, like was done this morning, we would also specify what the boundary, what the relative second homology class is of this disk, but we're not doing that. So then we define the differential graded algebra for L, and actually J as well. It's generated by the Reeb chords as well as the unit. We throw that in there. The grading, I gave a formula for it in a special case, in the one-jet space case. But morally speaking, it represents a kind of symplectic Lagrangian winding number called the Maslov index, also related to Conley-Zender index. The differential is going to be at this degree -1 operation, which we define on the generators by looking at all moduli space which are called rigid, but anyway, that means their dimension is 0, and counting these guys, and then using them as the coefficients in front of this word in the algebra, B1 times B2. So that's on the generators, and then we extend it to the full DGA via the Leibniz rule, or the sign Leibniz rule, if we're talking about coefficients with signs. So we could define this, or we could try to define it, but then we have to actually make sure it's a legitimate thing. And so, at least in the case that I'm interested in these sets of talks, the one-jet space of a smooth manifold. Indeed, this is well-defined. D is a well-defined thing. D squared is 0, and the differential graded algebra is appropriately invariant under all the choices you make, as well as under changing the legendrian, deforming the legendrian. And then we also talked about without doing any moduli space, well, at least, I mean, they are moduli space, but without having to use the word moduli space, I should say, but kind of a more combinatorial nature. In the case where we're dealing with standard contact R3, we can, instead of counting these holomorphic disks, count these immersed polygons in the complex projection of M. And then at the very end, I talked a bit about some successes and failures. And basically, if this differential graded algebra has an augmentation, that's a map from the differential graded algebra to the ground field, the ground ring, thought of as a DGA. If there is such an augmentation, you can do all sorts of computations with this thing. I didn't talk about those, but you can, and you can extract lots of geometric results getting large classes of Legendrians, which are not distinguished by any of the traditional invariants, but are distinguished by just little pieces of the Legendrian contact homology. On the other hand, there was this other kind of Legendrian, which is kind of the higher dimensional analog of a stabilization, something like that. I briefly talked about it. And those are called loose Legendrians. And in that case, the presence of this thing actually completely destroys the DGA. It's completely trivial. 1 is equal to 0 in this homology, I should say. Homology of the DGA. And in fact, with good reason, because if you have one of these little pieces, this loose Legendrian, it's actually a very flexible thing. It's completely determined by its formal class. Okay. All right. So for the next, so that was kind of like an introduction and some applications of Legendrian contact homology. So for the next 2 talks, yeah. In dimension 2 or higher, oh, killed? Yes, there are, in any dimension. What's not known is if it's like, if there's an actual generator such that dA equals 1 in dimension 1. But in dimension 2 or higher, that's now been shown. So if you are going to have some holomorphic curve invariant, you're going to need more than just the Legendre, the DGA. I don't know what. Right. I mean, there's lots of, this was actually the part that I didn't get to, but there's lots of small little extensions. I don't want to say small because each one is a lot of work, but you know, that push the boundary beyond this. So like, for example, one of the things we talked about was the number of double points, and that's bounded by the sum of the Betti numbers. That's now also bounded by the stable Morse number, which is a little more refined than the other things are different moduli space, moduli space of higher dimension, you know, trying to extract invariants from. Okay. Right. So today I was going to talk about not contact homology, because that's kind of a nice connection to topology and physics and an application of this. There's a lot of combinatorial computations done in it already. And then tomorrow I was going to talk about cellular Legendrian contact homology, which is an attempt at combinatorializing the count for higher dimensions. Well, at least dimension 2, the Legendrian surfaces. Okay. Right. So where to begin? Okay. So let me just. Well, okay. So supposing we have now not just a smooth manifold, but a metric. So a smooth Riemannian manifold. Then you have your cotangent bundle, which you normally write as this d of lambda. This is the Louisville form, the canonical 1 form, which in coordinates I was calling PDQ, or maybe I was calling it YDX, where y is momenta and x, the x are position coordinates. And then you have, there's also the unit cotangent bundle. Which is, I'll denote by S, I guess is what Somnath was using in his evening section. So this is pairs, well, points in the cotangent bundle where the covector is length 1, magnitude 1. Okay, and this thing has a contact structure, has a natural contact structure and form given by the kernel of this Louisville form restricted to the unit covectors. Okay, and now, now suppose I take any dimension smooth submanifold K in this Riemannian space. And let's let LK be the covectors which kill the tangent vectors of this submanifold. So this is 0, eta v of 0 for all v in the tangent space of X. Okay. So you can check, maybe we can make this exercise. First of all, the dimension of LK is n minus 1. And second, the tangent space of LK is inside this contact distribution. So therefore, LK is legendrian in the unit cotangent bundle. Right. And in particular, if K is smoothly isotopic to K prime, then LK is legendrian isotopic to LK prime. So if the legendrian contact homology of LK is defined, so for example, the main example is when X, when it's defined, then it's a smooth invariant, differential topology invariant for K. So you can use legendrian contact homology to study problems in differential topology. So far we've defined it for one-jet spaces, and here we're looking at unit cotangent bundles. Now in the special case, if K is in Rn, then the unit cotangent bundle of Rn, which I'm going to write in terms of coordinates, let's say Q and P. Okay, so you think of this is an element of Rn, and this is an element of Sn minus 1, the unit covectors. Well, is actually compactification to the one-jet space of Sn. And the map is, okay, you just send, so this is again, so Somnath is doing this in 3 dimensions, so I'll just write it down again, but also emphasize it could be done in n dimensions. You send this guy to your Sn, so remember this is, remember the one-jet space of Sn, minus 1, is the cotangent bundle of Sn minus 1 cross R. So this is going to go to the base coordinate. The next one is Q minus Q dot P. So here I'm thinking of these as, as vectors in Rn. So P is both in Sn minus 1 and in Rn. And then finally to the real number Q dot P. So also I'm using here the dot product because I've got a metric on Rn. Okay. So this actually, not only is this compactification, but this takes the standard Louisville form here. what was I calling it, lambda, to dz minus, let's say this is, again, I'm going to use coordinates x, y, and z, local coordinates, dz minus x, y dx, the coordinate system we've been using. Okay, so in particular, so if it's defined, then it's smooth invariant. So for example, if we're talking about submanifolds in Rn, this Legendrian contact homology gives us smooth invariants. Sorry, invariants for these submanifolds. Okay, so I put K down for a reason because we want to think about K as a knot and Rn as R3. Let's see. So, right. So, I'll make it a definition. Well, yeah, okay. I'll maybe make it a theorem. So, actually, let me make sure. So actually, I had to rearrange this talk so that it was in a nice natural order, but now I want to make sure I have enough time to get through the stuff, so it's all disjointed. So what am I doing next to make sure? First, I'm going to waste a bunch of time figure out what I'm doing next, so I don't have as much time. Yeah, okay, let's just do this part. Okay. Yeah. Okay, so if K inside R3 is a knot or link, smooth, then the Legendrian contact homology of this Legendrian, so again, so here think of, so LK, we're thinking of it as a Legendrian in, the unit cotangent bundle of R3, but this is actually also a Legendrian in the one jet of F2. Then this has the same combinatorial formulation that Somnath described. In the evening. That is, the LCH of this Legendrian is equal to the knot contact homology of this knot. So I won't. It was, it's quite a Herculean effort to describe that thing. But I'll just. So I'm not going to describe it again, but I will just say a few things, just for those that were there in the evening. Basically, you take the knot and you braid it around the unknot. You can always do this. So something like that. Okay. This is supposed to be a braid, by the way. And you take this braid word, and it becomes part of the differential. This is used, appears in the knot contact homology differential. So this was pretty complicated combinatorially, and it's something you can't really do by hand, but there are computer programs to extract invariants from it. There's also, at the very end, Somnath talked about a kind of topological version to represent at least the degree zero part of this. So KCH also has a nice topological description. KCH, let's say 0 in degree 0, also has a nice topological description using Liang-Yang's chord algebra, which looks a lot like the knot complement, but it's not. It isn't that. It's an algebra. It's looking at looking at kind of open strings on the knot, and the knot complement subject to some rules about what happens when a string crosses through a knot. Kind of split the string and so on. So that has a nicer topological description. This has maybe a computer implementable thing. Okay, so one of the outcomes of this from, so Eng showed that his knot contact, this combinatorial invariant detects the unknot. This is the smooth unknot. That is, right, its value is different on all other knots. So if you see it appear, if you compute some, if you plug in a knot and the output is the knot contact homology of the unknot, you know that your knot is the unknot. That's what I mean by detects. And so in particular, so LCH of this detects the unknot. So in particular, we have the converse to this statement. So K is smoothly isotopic to the unknot if and only if this conormal construction, I forgot to mention, this is called the conormal construction, is legendrian isotopic to the conormal of the unknot. And this was actually recently, I guess it's, not officially vetted, but it's been a recent preprint actually shows that this is true for all knots using sheaf theory. So in fact, K is smoothly isotopic to K prime if and only if their conormals are legendrian isotopic. So, okay. So, all right, I can throw out some open questions here. Of course, these are definitely not, easily manageable. But so that this discussion, this result was just done in R3 because it's kind of the easiest thing to draw. I mean, you're working with one jet spaces of S2, which, we saw last time, I can draw some of these legendrians because you're in the zero jet space of S2, but there's a natural question of how to generalize this. So, okay, so like for example, the place to start, although even this is hard, is a smooth surface also braids, well, let's call it sigma, braids around a smooth surface in R4, braids around the unknot. Well, unknot. Just like you can braid a smooth knot around the circle, you can braid a surface around S2. And so you can try to, can one repeat the, generalize this theorem to get a combinatorial version of the LCH of this lift. And if you could do that, I'll go even further to something even, can you prove something like this? That two surfaces are smoothly isotopic if and only if they're Legendrian lifts are Legendrian isotopic. And again, one direction is obvious, this direction. You just lift the isotopy at each stage, and you get a Legendrian isotopy upstairs. It's the other direction, which is perhaps false, I don't know. That's a recent paper by Vivek Chende. Actually, I should mention. Okay, yeah. Yeah, I haven't really been good about writing who's proved what. My apologies about that. So this was done by Chende using sheaves. And then it was also done by Ekholm, Eng, and Chende using Legendrian contact homology. Although in that case, it was more than the Legendrian contact homology of LK, but also some kind of fiber. So you kind of have to throw in another Legendrian and consider a more advanced DGA. The DGA of just LK alone, they didn't know if that was enough. This one, it's one of those ones which is essentially true, but it relies on some technology which has not been totally ironed out yet about the morphism statements of DGAs. And this one I don't pretend to understand. I'm still in the learning stages of sheaf theory. Okay. I don't know that. Yeah, I mean, I would think anything that, I mean, it's such a big invariant. It's got to, I mean, it probably, should detect everything, but I don't know what's known, like how far that's been done. So my first answer would be that it's not known. Okay. Let's see, was there anything else? Okay, I think that's all I want to say about not contact. Well, besides the proofs or some constructions about it. Okay. Where am I supposed to go next? Right, okay, so. Oh, actually, I could put a little, one more open question here. So, what's the name? So Eng and one other guy. This chord algebra can also be defined in higher dimensions. So one could ask to directly compare the two. I don't know. Did you guys do that, Yanko? In higher dimensions, do you look at the chord algebra? Where the submanifold, it's not a knot in R3, but a codimension 2 submanifold. Oh, okay. Okay, let's throw it in there then. So the chord algebra is also defined for any. Oops, this is 3. chord algebra is defined for any codimension 2 smooth submanifold. Can it be recovered by Legendrian contact homology, as was done in this for the not case, if you want to skip the combinatorial approach. Okay. All right. So the next thing I wanted to talk about is kind of a refinement of not contact homology. And again, since I'm not giving the combinatorial definition, you can just think of not contact homology as this, the Legendrian contact homology of the conormal lift. So I'll call this transverse not contact homology. So I need to give some definition. Well, a definition first. So we say that a knot K inside M3 inside any contact manifold is transverse to the contact structure, is transverse if exactly that. If when you look at the tangent bundle at any point, you're transverse to the contact distribution at that point. Sorry, it's not the tangent bundle, the tangent space. Oh yeah, tangent bundle. So it's kind of the exact opposite of being Legendrian. Legendrian, remember, you're tangent to the distribution, and now I'm asking you to be transverse to the distribution. But despite being kind of the exact opposite, by the way, this is another oppositeness is that this is an open condition, whereas Legendrian was a closed condition. But despite being kind of dissimilar in that way, there's still a correspondence in some sense. So transverse knots correspond to Legendrian knots. They're not the same, but there's a way of associating one to the other, modulo positive stabilizations. And to say something a little less precise, any Legendrian knot can be C0 perturbed to a transverse knot. Not C1, of course, because the tangent vectors are totally different, but C0. Okay. So this is kind of like a parallel kind of world that contact geometers study. Instead of Legendrian knots, they study transverse knots. There is a kind of a theorem that we have for smooth knots. Remember, any smooth knot can be braided around the flat unknot. Well, if you take MC to be R3, but we're going to, rather than the standard contact structure, we're going to take this rotated, this symmetrically, this S1 symmetric contact distribution. So I'll just kind of make some vague attempt to try to draw this. So you kind of, as you go out in the radial direction, you twist, and you twist the same, you twist by the same angle based on how far you're out, not in what your theta coordinate is. So I don't know if that's anyway, so this is from lecture 1. Okay, so in this case, we can take this flat knot and this is transverse. There's always hitting the contact distribution at the same angle. Then any transverse knot here can braid about this flat unknot. Here. So by that I mean after a transverse isotopy, of course. A priori, it could be who knows what. And there's actually a more general, result now. This was due to Benniken, but more recently, I'll just say this, but I'm not going to define it because I don't need it. But if you know this, there's a similar story for arbitrary three-manifold, contact three-manifold, using what's called open books. There's a way of expressing a contact distribution in terms of something called an open book that supports the contact distribution, and then you want to be transverse to the pages. Anyway, so it's not just in R3, you can do something like this. Okay. So we'll just think of transverse knots as being braid in this, remember that this is contactomorphic to the standard contact structure, or contact isotopic. So it's not just some random thing I'm picking up. Okay, and so we have this. For transverse knots, we have this one classical invariant. So besides, of course, the knot type, the smooth knot type, we have one classical invariant for transverse knots known as the self-linking number. Which you can define as, okay, so let me write this down. You can define it as the signed sum of exponents of the braid word minus the number of strands of the braid. So, like, for example, if I have some sort of braid which has something like this, then the braid word here is sigma 1, sigma 2 inverse, because here I'm switching, I hope I got this right. That doesn't look right. I'm switching strands 1 and 2 one way, and I'm switching strands 2 and 3 another way. That's the inverse. And so in this case, here I've got 1, 2, 3, 4, 5 sheets, and so that's 5 strands, and the signed sum would be 0. Okay. So, right. Okay. Actually, let me do a. Actually, this is a link. So let me do something even easier. Okay. So here, for example, the self-linking number is -1 because I just have one strand. Here, it's also -1, and here it's 3. So this says right away that this guy is not transverse isotopic to either one of these two. And in fact, so as was discussed earlier, sometimes the classical invariants are enough to detect legendrian knots. That is also true for transverse knots. The self-linking number is enough to detect transverse knots when the knot type is the unknot. This might be a little out of date, sorry, but if it is. The torus knot, torus knots, figure 8. Some twist knots. However, it's not enough for other knot types. So for example, like including other twist knots. Including what? Cables of torus knots. I don't know. Okay, and so there is one there was a holomorphic curve invariant for transverse knots. So one tool to distinguish transverse knots arises from what's known an entirely different holomorphic curve theory than I'm talking about, but it may be in one of the evening sessions implicitly when you do Lagrangian floor homology. It is an example of Lagrangian floor homology known as not floor homology. So this is a popular flavor of floor homology used by people in knot theory and in low-dimensional topology. I forgot what it's called, like loss invariant or OST invariant. So there's another. So I want to talk about another one, which is this is a kind of Lagrangian floor theory flavored invariant. So the one I want to talk about is a legendrian contact homology flavor invariant, basically coming out of the knot contact homology. Oh wow, I have an hour and 25 minutes left. Perfect. Does anyone know what I actually have? 45? Okay. Knew that was too good to be true. All right. Okay. So, what do you mean by it? Well, there's a transverse knot invariant that I'm going to talk about, yeah.
Yes. So they look at one particular element.
Oh, it's not like that. So yeah, so just the contact invariants and the Legendrian invariants, they look at one particular element, whereas in Legendrian contact homology, you look at the whole structure. Yeah. Okay, so let me just talk about so another one is what I'll call transverse knot contact homology, which works as follows. Let's take the conormal lift of the contact structure itself. So I'll denote the conormal lift of the contact structure. Okay, conormal lift of C in R3 to the unit cotangent bundle of R3. So denote the conormal lift by nc. So this is, so we're going to do the same thing we did for a submanifold. We're going to look at all the points, in this case all the points, not just all the points because there's no submanifold. So all the points in this unit cotangent bundle. So x just has to be in R3, no constraint there. And eta has to kill all vectors in the contact distribution for R3. So now this is going to be a bit confusing because I have a contact distribution in R3, that's a two-dimensional plane field, which I'm calling C. And I also have a contact distribution in this five-dimensional manifold, and I'm just going to not call it anything so that you don't get it. So this one will be called C, and the other one will be called that. Okay. So this is actually, so maybe it's drawing a picture just to keep track of these conormal lifts. So like, for example, let's say I'm at here's R3. I'm at a point, I was using Q. I'm at a point Q, and here is the contact distribution for R3 at that point. And now I have a transverse knot. Okay, so it has to hit the plane transversely. Okay, and we have two different, okay, and right, and what does it look like? What does the conormal lift of this guy, the knot, and the conormal lift of the contact distribution look like over in the appropriate fiber? So, so the fiber is going to be an S2. That's our fiber for the contact manifold. So the conormal lifts NC and LK in this fiber. So, all right, so I'm going to now, by using a metric, I'm going to draw vectors and I'm going to draw covectors as vectors. So if I look at the knot, I want to look at all these covectors, unit covectors. Okay, so that let's say that they're here. So I have a circle worth of unit covectors. If I look at the contact distribution, okay, I shouldn't necessarily draw. It's not necessarily exactly this knot. It might be like there and there. So those are 2 points. Again, these are a unit covector here and a unit covector here that kill all the tangent vectors to the contact distribution. Okay, so that's what it looks like over a fiber. Now, you might look at this and say, well, orange looks bigger than red. But this is a very special point Q. This is a special point Q. This is a point Q that's on the knot. If I'm off the knot, my fiber doesn't have any orange, but it still has 2 red points because my contact distribution is still at that point. So in fact, the orange is 2-dimensional and the red is 3-dimensional. Another fiber. Well, okay. Okay, so also notice that, well, yeah. So maybe I should write that down. So note that, first of all, this is 3-dimensional, what I said. Second, NC can be written as a positive part, what do I call it? Yeah, positive part and a negative part. So there's always going to be a north pole and a south pole because this is a co-oriented distribution here. Contact distribution. So there's always an up arrow and a down arrow. And then finally, this and this are disjoint. you're never going to have a red point on top of an orange circle. There's one more. I'm going to make this as a less obvious claim, but that is if you take this three-dimensional guy and you cross it with RT, okay, so this is now sitting inside the unit cotangent bundle of R3 cross RT, which is also, that's the symplectization of the unit cotangent bundle. It's also the symplectization of the one jet space of S2 cross RT. I claim that this is actually J-Holomorphic, four-dimensional. J-Holomorphic in the symplectization. For one of the J's that, for the J's that we have to choose from when studying our moduli space of curves. Okay, so we're going to define now a kind of filtered version for the conormal lift of the knot. It's actually doubly filtered by the following. So I take dA. So first I make it look, I count the dimension of the moduli space of A, B1, Bk is 0. So I look at zero-dimensional moduli space. I count the number in this moduli space. I multiply it by the word B1 through Bk. Okay, so far this is exactly like legendrian contact topology. And now here I add this extra thing. I'm going to add some formal variables here. U plus and U minus, where U plus minus are formal variables in the coefficient ring. With degree 0. Let me explain n plus and n minus. And where n plus or n minus is equal to, you do a count of the image of U. This is in my mod space. Yeah, that's actually not good notation. I should say sum over U in this moduli space. Yeah. So you look at the image of U and you intersect it with this conormal lift, the positive or negative part, across RT. So this is a disk, so its image is two-dimensional, and this is four-dimensional. And we're sitting inside the symplectization, which is six-dimensional. So at least from a dimension count, this is something it's a zero-dimensional thing, and I can count it. There's another thing you can actually state because of, okay, so this is so this intersection is zero-dimensional, so I can count it. But I also want to say, because both are holomorphic, all counts have positive sign. I mean, actually, to really prove that you can project down and have a two-dimensional thing and another two-dimensional thing inside a four-dimensional thing. And so, oh, this is something else. Okay. So D is filtered by both U plus and U minus. That is, D reduces the count. Yeah, right. Okay. So far, this there's no actual use of the transversality yet, the fact that the knot's transverse. I could have just done this for a smooth knot. So all I did here is I introduced this idea of lifting the contact structure and then, and then making a count. So the fact that it's transverse comes in here. To prove that d squared equals 0, so this is kind of like the compactification picture from, how this count is? Oh, how I get the, okay, so going back to here, we saw that over every fiber, well, or even just going back to here, there's 2 arrows. And because this is a co-oriented distribution, these arrows are this is a globally defined thing. So N really is disjoint union. Okay, so to prove d squared equals 0, we're going to do the same the kind of marked point argument that was done in the previous talk at the very end, although more generally. What you want to do is you want to say, okay, supposing you want to show like supposing you want to show how to prove d squared equals 0. So say you want to show something like this. D squared A u plus cubed c is 0. So this means that the coefficient of this word in this expression is 0. Now you have to do that for every a and every term to get that d squared is globally 0. Okay, and the standard way you do this in like Morse theory, you say, okay, let's look at the moduli space of a u plus 3 cubed. U plus 3 cubed times c. Okay, so here's A, here's C. It's a one-dimensional moduli space, and it has 3 marked points corresponding to intersections with n plus c. Okay, that's how you count how it's that count which corresponds to this this coefficient. Okay, and what happens when you're looking at one of these moduli space? You look at the compactification of this, and it might have something like this, or something like this. I'm going to ignore all the other bubblings that I talked about last time and just focus on what happens to these points. And let's say that 1 point goes here and 2 points go here, and in this case, all 3 points go here. This would be an expression dAB2 times dB2 u plus cubed c. This would be an expression dAU plus 1 B1 times dB1 u plus 2 times c. So basically this coefficient is determined by counting these kind of curves. This coefficient is determined by counting these kind of curves. And then the product of this is equal to the number of these broken curves. Okay. That's kind of the gluing compactness idea. And so then you see, okay, good. So this is equal to this plus that. And since I'm only counting mod 2, there's always going to be an even number of boundaries. I get this number plus this number is 0. And I'm done. Okay, where I use transversality, and this is the fact that the knot is transverse, I mean, and this is something that didn't show up in the morning, is that you want to make sure that as you go in the limit, one of these yellow points can't run away to the boundary. This would be bad if you had something like this. I don't know, 1 and 1. Okay? And that's exactly where transversality is used. Not transversality, the not being transverse is used. It's used to say that these intersection points cannot run away to the Lagrangian boundary, which is expressed by yeah, maybe I should say it this way. NC cross R T intersection LK cross R T is empty. So an intersection point of U with this guy cannot run away to this boundary because this boundary does not intersect this 4 manifold. Okay. Sorry if that was, I don't know, if any questions about that? That was a little bit improvisational. Yeah, so counting, I mean, even counting 2, like I could have 1 here and 1 here, and I would be in trouble. Counting mod 2 is not going to help it. Are you asking how does counting mod 2 come in here? Or?
Yeah,
A lot of pictures, but there'll be an even number because there'll be the number of boundary components of this one-dimensional space. So the number of boundary components is always 2 for any one-dimensional space like this. It's also 0 if you count it appropriately with signs. Okay. So let me just throw out a couple of open questions from this. Oh, yeah, actually, let me make a theorem. Right, okay, so I guess the theorem is that transverse not contact homology is also combinatorial. Basically, looks like the not contact homology with these braids. Braid word in it, plus some U plus minus factors added in. So it's another combinatorial invariant, and you can do whatever kinds of things people do to simplify DGA computations or implement them on a computer. And you know, you get a new combinatorial invariant for transverse knots. So it's a big invariant, and I don't have this on my writing anywhere, but I will mention that so it's known that the topological type, the self-linking number, and this not floor homology invariant are not enough. There are examples where these are all the same, but the transverse not homology can still distinguish. So it's open is the topological invariant and the self-linking number, and the transverse this enough to distinguish knots, to detect all knots. Well, let's say distinguish all knots. Okay, so that's one question. Another question is, I'm just about to erase this. So you could do this same thing for a conormal, you can do the same braiding around any three manifolds, and you can do this same conormal construction in the unit cotangent bundle. Of course, the problem is then, if it's not going to be a one-jet space, is the theory well defined? But nonetheless, sometimes it can't, you know, there are efforts towards making that well defined. So, so another question would be, this is one. Another question would be, repeat this. So is transverse knot contact homology well defined for transverse knots in an arbitrary three manifold? I mean, you can start with the same approach, and in principle, there's no reason why it's not, but in practice, it's a different story. And then you could also talk about this in any dimension. I mean, you can say, well, let's say you can define some submanifold in an arbitrary contact manifold to be transverse if, again, the tangent bundle for the contact structure is transverse to the contact distribution. Sorry, the tangent bundle for the submanifold is transverse to the contact structure. And so, again, you'll have this guy and this guy don't intersect, which was needed for d squared. The problem is that over here we had, where was it? We had holomorphic curves, which were two-dimensional, and this conormal lift crossed R, which is four-dimensional. And we can intersect that and count those intersections. Now, this guy is not going to be the right dimension. So note that and I'm talking about even if you're in R2n, so don't worry about, yeah, let's make it R2n. Let's keep it simple. Don't worry about the Legendrian contact homology being well defined or not. So you can define, but anyway, so the problem is that in this case, if you still have that this conormal lift intersection of fiber is 2 points. Okay? There was nothing about 3 dimensions here to make these 2 points. It was just that it was codimension 1 that made these 2 points. This guy's still codimension 1. So that means that the dimension of this lift, either component cross R, is going to be 2n plus 2-dimensional. Because you have 2 points over the entire contact manifold, which is 2n plus 1, and then you add 1 more for that. But so if U is in a moduli space of dimension 0, then U and this guy will not intersect generically. It's too small. You've got 2 dimensions and 2n plus 2 dimensions, and you're trying to one possible solution, right? So right, this is 2, this is 2n plus 2, and this is not equal to the dimension of the cotangent, the dimension of the symplectization of this. which is equal to, let's see if we get this right, 2 times 2n plus 1 minus 1 plus 1. Okay, so what you would have to do if you wanted to get this theory to work is you'd have to, so you need to look at higher dimensional modular space. So that instead of looking at, points in the moduli space, whose curves gives you two-dimensional things in the symplectic manifolds, you'll be looking at larger moduli space, the union of whose curves will give you larger dimensional things in symplectic manifolds, such that this intersection of, and then hopefully you define some invariant and you can, the d squared equals 0. This picture is still morally true. Points are not going to migrate to the boundary. Maybe. Yeah, okay, so the yellow points are where this disk is supposed to be in the symplectization. Maybe I should have written it this way, drawn it this way. So I have my symplectization, and here I have some disk, okay, which in this case only has one positive puncture and one negative puncture. And then I also have a four-dimensional guy in here, which is n plus minus c cross r, two four-dimensional things. And the yellow point would be, pardon? Yeah, I didn't mention that part, but yes, they can't migrate to the ends either. Oh, I'm sorry. No, this guy, no, it's non-compact because it's cross R.
Okay, so it does not intersect the side boundary, but it goes to the top.
So when you say it, this definitely goes to the top and bottom. However, a puncture cannot go to the top or bottom. I didn't.
Those are not intersections.
I'm sorry, intersections. Yes, the intersections cannot go to the top or bottom.
But if there is like a top, another floor, like you can't intersect.
Like this one.
Yes.
Yeah, so you could have a breaking, and it's not going to go near a puncture, but it'll be on the other part. So when you say top or bottom in SFT, you have to be a little careful because you could always shift up or down and say what is top is now center. So when I mean top or bottom, I mean back in the domain. I mean near the puncture of the disk. So so here are the pullbacks of the intersection points. Sorry, I keep saying puncture. I mean intersection points. Here are the pullback of the intersection points to the domain, and I claim that the puncture, the intersection point, cannot migrate to a corner or to a boundary. Okay, so top from the point of view of the range, which is not top from the, yeah, so you could have something like this. Yeah. Because there's only 2 points. A lost one. And somehow, in some finite time, it went to the boundary and disappeared. I'm saying that can't happen because the knot's transverse. Cannot lose them, yeah. So like in the closed case, there wasn't this issue. There was no boundary for the points to go away. In the open case, the boundary case, you have to have something about the boundary that keeps the points from running away, from running off the boundary. There's no bubbling like that. That would make the LCH not a good theory. It wouldn't working. Yeah, there's none of this because the Lagrangian is exact. And there's no sphere bubbling because the symplectic manifold is exact. And the other things are gotten rid of. Was that it, or do I have more time? I forgot. 15? Or when are we supposed to end? 1, okay. All right. Okay. So So what can I say? Okay, so it's good I restructured it. So, all right. All right, I think what I'm going to do is just talk about one ingredient in this proof of either of these theorems about the not contact homology being the same as legendrian contact being a cohomological lift, or this combinatorial version for not contact homology. Because part of the theme of what I wanted to talk about was how, well, actually, the underlying theme of really what I wanted to talk about was how this pseudo-holomorphic curve invariant, yes, it's useful, but also in some cases it's computable. So, and these are all these are basically computation results, and then also the third talk. So, I think what I will just have maybe time to say is this result of Ekholm's, which is, all right, so a main ingredient to KCH and transverse KCH and cellular LCH, which is tomorrow, is this theorem by Ekholm, which says that it's not just a person, he's an actual theorem. It's not just somewhere between a proposition and a theorem is an Ekholm. Oh, let's see. Theorem Ekholm, which says that with some hypotheses, which I won't spell out, counting rigid J-Holomorphic curves for LCH in, this is the case where M is the one jet space of some manifold, is equivalent to counting gradient flow trees. Which I'll abbreviate GFT. And these generalize Morse flow lines. So, was there a section on Morse theory, or by any chance on Morse? Oh, today? Today, okay. So maybe I won't, since I only have an hour and 25 minutes left according to that clock, maybe I won't spend time on that. Okay, so, but let me just draw a picture of what I mean by the correspondence. And then I may not have time to actually say what a gradient flow tree is, but hopefully this picture will give you some idea of what I'm talking about. Okay, so so what are gradient flow trees? Okay, so let's consider a one-dimensional LCH computation. Okay, and why one-dimensional? Because we have Chekhov's formula there to find the holomorphic disks. So we already know what the holomorphic disks are. They're easy. You see them. They're immersed polygons. So for example, I'll do two examples. So we look at the projection, the pi n direction, the Lagrangian projection. Okay, so we have something like this, say, and we have these two holomorphic disks. We have a record. Uh-oh, I'm starting to make that noise, aren't I? It's because I haven't shaved. I didn't bring a razor. I would have to check it in a bag, so it's going to get worse and worse. Yeah, so remember, dA is equal to 1 plus 1. And here are our two disks. And maybe here's another example. So leave some space under here. I want to, if you're taking notes, I want to draw a front projection. This is in the front projection. It's not really a disk anymore. Over here we have, I don't know, let's draw, okay, I think I got the derivatives right when I did this, the partial derivative right, I mean single derivative. Okay, so here's A, C, and B. And here we have, for example, dA equals BC. So this is a positive puncture, a negative puncture, and a negative puncture. And we have this immersed polydisk here. Okay, now here I'll try to draw the front. So the front is going to look like something like this. Actually, since I have it positive, it's going to look like this. Not that it matters so much, but I did draw it with y as positive. This one's going to be more complicated. Yeah, let's just forget about the axes. Okay. So I'm going to try to trace out the boundary of this disk here. Okay, so first I have a graph that looks like this. Remember, this is y and this is z. So I have here the y coordinate is positive but decreasing. That means the z coordinate is increasing but concave down. Okay, so that's why I drew it like that. Then I have a chord, which I'll indicate like this. I'll draw these chords as if they were here. And then I'm going back. So that looks like this. And then I hit this little curve. This is like a cusp. And here's another curve, another cusp. And then I go along here. And I hit a cusp, and then last cusp. Okay, so that's B, C, and A. Now, what I would like to do is I would like to kind of draw this disk. Think of the what I did is I looked at the boundary of the disk and I represented it as a boundary of legendrian. And here's the boundary of the disk, which I represented as another curve on the front. And this disk here, I'd like to think of as representing some kind of map, a map. This is the domain, the GFT domain, from a critical point to, well, to just nothing. So this is, you can think of this as a flow of the gradient of f1 minus f2. Where here, this is the graph z equals f1, and this is the graph z equals f2. So, this is the true disk inside C. This is the flow line in, actually it's really right here. This is going, actually this is the negative gradient flow. That's what we tend to do in Morse theory. So this disk right here corresponds to this negative gradient flow. And why is that? Because if you take the lift of the legendrian, the two lifts, here and here, given by F1 and F2, it matches the boundary of the Lagrangian, of this disk. Sorry. Over here, it's more complicated. It's going to look something like, okay, you start at a critical point of F1 and F2. Shoot, I don't have enough room. Okay. So this is F1, F2. Then you pass a critical point of F2 and F3. And it keeps going something like this. Splits here. Okay, here's your critical point, B. This is just a kind of running into a cusp edge. I'm already off. This is F1, F1, F4, F5, F5, F4, F3. Okay, so basically what we've done is we've taken this disk and we've represented it as a kind of a patchwork of gradient flows of differences of functions. So here it's a flow between F1 and F2. It becomes the flow between F1 and F3 and a flow between F3 and F2. So there's another pair of two pairs of functions and so on. And this is essentially what a gradient flow tree is. So rather than this, okay, it doesn't look easier in one dimension. In one dimension, I just saw the disk. I could have just shaded this in, and here it looks like this complicated thing. It's got these aspects that are not really recorded in the disk. However, this becomes a lot easier in higher dimensions when you can't see the disks anymore, but you can still play with functions and differences of functions and intersections of stable and unstable manifolds and so on. It's a finite dimensional analytical problem. I think, right, not really a great ending point, but probably what I'll do is I'm just going to end it there without giving a formal definition of a gradient flow tree or how we use these to make either of these the rest of the computations. But I will refer back to these gradient flow trees in the next talk when we're dealing with general surfaces. So, actually, let me, since I've got 2 minutes, at least let me throw in a couple of open questions. Nah, let me not. Let me let you, 2 minutes early, we can get some more time to eat. So I'll just end it there.